Section 5.3 is the fundamental theorem of calculus. Here we want to relate the concept of an area function to what we've been talking about because it's crucial to the discussion or the connection between derivatives and integrals. We start with a continuous function, f of t, and it's defined for t values that are greater than or equal to a, where a is just some fixed number. The area function for f with left endpoint at a is denoted as cap a of x. It gives the net area of the region bounded by the graph of f and the t-axis between t equals a and t equals x. That same net area, we already know, is related to the definite integral. So we are now connecting, formally connecting that net area and the definite integral here. All right, so the independent variable of the area function, a of x, is also serving as your upper bound. And then notice that you have a variable of integration that is not x, it's just some dummy variable. Anything that isn't x would have sufficed. We just don't want to reuse x since we've already are using it elsewhere in the problem. All right, this next figure should relate the net area to our continuous function. So what we'll see happening here, hopefully we will, is you'll see this continuous function, which is f of t, it's the darker function here, and we're going to shade under that function. And as we shade under the function, right, we're shading the area between the curve and the x-axis. We're going to start adding those shaded areas up, and it would return a value for us, right? And then we should see that as these values accumulate, right, it will have an impact on our area function. So in other words, we are going to shade under this graph. You can see the green, greenish blue area that's being shaded here. And you should also notice this red dot kind of sliding back and forth when I do this. This red dot is showing us how much of the shaded area, right, as we go on, we're accumulating all of this area, and it is impacting our area curve. So what should happen here is as we add more and more area, no matter if it's a whole lot of area like we have right here, or not so much, because if you look right here, this little white sort of triangular piece, it's not a whole lot of area under the curve, but it's still getting added to what we already have, and should make our area function, which is this function right here, should make it increase as we add more and more green area to it, right? But once we hit C, notice that our area function starts dropping, and the reason for that is that the area under the curve, or in other words, between the curve and the x-axis, is now negative because my curve is below the x-axis. So remember what's happening here is this curve, the f of t curve, right? We're trying to find the area between it and the x-axis, but it's net area. So if it's below the x-axis, it's going to return negative values, and those negative values will impact the overall area function, right? So as we add these negative values, we should see that our area function is falling. Our net area function, right, is falling because it's a cumulative effect, and we're adding those negative numbers in now. All right, so this figure shows how the net area varies with respect to x, and we saw that it increased until it got to c, but for values that were greater than c, that f of t function is negative, and so it was contributing negative values to our area function, and so we saw that area function decrease. So we're actually going to talk about that net area function then, so that we can jump into the fundamental theorem of calculus from there. So let's let f be a continuous function for t values that are greater than or equal to a, and we'll state that the net area function for f with the left endpoint of a is this definite integral where x is greater than or equal to a. The net area function gives the net area of the region bounded by the graph of f and the t-axis on the interval a to x. Let's use it and maybe that'll help. The graph of f is shown with areas of various regions marked. Let a of x, so the net area function, be the definite integral from -1 to x of f of t dt, and let cap f of x be a definite integral from 3 to x of f of t dt. These are both net area functions. Let's evaluate the following. A of 3, remember this was a of x equals -1 to x of f of t dt, and here we have cap f of x, 3 to x, f of t dt. Notice how these are the same variable, so if I replace this x with a 3, then this x has to be replaced with a 3 as well. And from this picture we can go fill this in. If it starts at -1 and ends at 3, right, starts at -1, ends at 3, then we're talking about this area. It's below the x-axis, so it should return a negative value. F of 3 says start at 3, end at whatever x you're plugging in, so end at 3. And this is actually one of our properties for definite integrals. We know that if your lower bound is equal to the upper bound, then the answer is 0. And that kind of makes sense. If you start at 3 and end at 3, there's no area for you to have shaded in. A of f, or A of 5 rather, says you're going to start at 1 and end at 5. Alright, well, if you start at -1 and you end at 5, you actually have two areas that they've shaded in that we need to look at. The first one starts at -1 and goes to 3, and it is below the x-axis, so it returns -27. But then you also need to pick up the area between 3 and 5, which we're told is a value of 3. F of 5 says start at 3 and go to 5. Well, if you start at 3 and go to 5, your area is just 3. A of 9 says start at -1 and go to 9. So -1 to 3 gives me a -27. 3 to 5 gives me this area, which is a +3 because it's above the x-axis. And then 5 to 9 is below the x-axis, or that area is anyway. And so when we add these up, you should get -59. And then we do something similar for f of 5, so you'll start at 3, f of 9 rather, you start at 3 and end at 9. So we'll have to break it into pieces, and we'll say 3 to 5 gives us that positive area of 3, but 5 to 9 is below the x-axis, so it gives us a negative value. Add them up, you get -32. These are negative values. They are net area. Remember, actual area cannot give you negative values. These are net area. let's take this a little bit further. So here we are given a picture of a line, f of t equals 2t plus 3, and we are saying to look at a lower bound of 2 and an upper bound of x. And between those bounds, if we shade in, we'll see that we are shading a shape that we are familiar with. It's a trapezoid. All right, we might not have a idea of how to handle this particular definite integral just yet, but we do know how to find the area of a trapezoid. We know that from high school or junior high, so we're going to use that to our advantage. All right, so I'm going to scroll down just a little bit here, and I'll reproduce this off to this side. Okay, so let's see. We know how to deal with this. If we want to evaluate a of 2, well, whenever we plug 2 in for x, here we should plug it in for that upper bound as well. So that means we would start at 2 and end at 2. And anytime your lower bound is equal to your upper bound, you know that the answer is 0. Okay. What about at 5, though? This one might be a little bit more difficult. So this says, okay, if I'm plugging in 5 for this x, I got to plug it in up there as well. Well, what would that look like according to this picture, right? This would have our lower bound of 2, but our upper bound would not be x, it would be 5. So let's see what that kind of looks like. I'm going to draw it down here. Well, I know that this is trapezoid, and I know how to find the area of a trapezoid. That is 1/2 little base plus big base times the height. Our little base is, the bases are always parallel to each other, by the way, so our little base is this guy right here, and I know its length, or I can find its length, by taking 2 and plugging it into the function. So back over here, I may not know exactly how to deal with this definite integral and bounds and all this stuff just yet, but I do know that this is exactly the same as the area under the curve, and the area under the curve looks like a trapezoid, and I know how to find the area of a trapezoid. It's 1/2 times the little base plus the big base. Well, here's the big base. Again, I can find its actual value by taking 5 and plugging it into the function. And then multiplying it by the height. The height is the distance between those two numbers, so 5 minus 2 gives me 3. And then I clean this up. 2 goes in there 5 times. Oh, that's not 10, that's 20. Sorry about that. I'm like, wait, how did I get the wrong number? All right, that's 30. Okay. I was doing that in my head already. Okay, so we got 30 right there as our answer. Now, what would happen if I wanted to figure out a of 200. I would have to do every bit of this work and this work again. What if I had to find a of 79? I'd have to do all of this work and all this work again. I really don't want to do that. So what I think I'd rather do is leave this as an x value and try to figure out if there is a formula that I could find that would maybe let me plug the 5 or the 2 or the 79 or the 200 into it and immediately pop out the answer without having to do all this work again. So bear with me. I'm going to do this work one more time, but instead of having this guy be a 5, I'm going to have it be an x. So I will have to erase a little bit just so I have enough space. Okay, I'm going to draw again. So this is f of t equals 2t plus 3. And it's got a lower bound of 2 and an upper bound of x, and we want to find the area under that curve. Okay, it's a trapezoid. We don't know how to do the calculus on this guy just yet, but we do know how to deal with the trapezoid. It is 1/2 the little base. Right, well, the little base is this guy, and I find his height, or his length rather, by plugging him into the function. Plus the big base, which is this guy, and I find him the same way. I plug him into the function. It doesn't spit out a number, it spits out a variable, but so what? Times the height. Well, the height is the distance between those two values and the distance you find just by subtracting. So x minus 2. Doesn't feel right, but this is how we do it, I promise. Okay, so we got 1/2. Let's see, 2x plus 10. Okay, let's distribute this 1/2 to each piece. And then we can FOIL this. And, you know, just for grins, let's see if this does what I think it's supposed to do, right? Because what I think this is a formula that if I was given a number, I could quickly plug the number into this formula and it would spit out an answer. Let's just check to see if it seems like it works. If I were to take 5 and plug it in here, I would get 5 squared plus 3 times 5 minus 10. Hey, that seems to work. So if I wanted to know what a of 200 is, I just plug a 200 in. If I want to know what a of 79 is, I just plug a 79 in. And let's look at the next thing we're told. Compare the derivative of a. This is interesting. Compare the derivative of a, which we have up here. So let's find that derivative of a. Derivative of a is the derivative of this. Compare that to f. Well, f is right here. So, it looks like the derivative of a is equal, almost, it's not quite equal to f of t, it's equal to f of x. In other words, it's equal to f, but I have a x as my variable instead of t. Okay, well maybe we can make some correlation or some correspondence between that and the other things we know, or the fundamental theorem of calculus. I think we're headed somewhere with this, so hang on to that for a second. Okay, fundamental theorem of calculus part 1 says if f is continuous on a closed interval a to b, then the area function, cap A of x, is equal to the definite integral from a to x of f of t dt. And it's continuous on that closed interval, and it's differentiable. The area function satisfies the derivative of cap A of x is equal to f of x, or equivalently, so this is what we just discovered, right? That if you have this area function and you take its derivative, then what you end up with is your integrand evaluated at that variable. That's what we just saw in our previous example. Another way to write this is to say, okay, here's this function right here. If I take its derivative, so if I take the derivative of a of x, you see the prime, a prime x then. But if I take the derivative of the left side of the equal sign, I've got to take the derivative of the right side as well. So that's where that dx is coming from. And then they're just taking this statement right here and throwing it in, right? Because you already have the a prime, so they're just adding in this extra stuff here. All right, so this means that the area function of f is an antiderivative of f. All right, well, how does that help us? We'll come back to part 1, right? Part 2, I think, is a little bit easier to understand, and we'll use it to maybe help us understand what's going on with part 1. All right, part 2, the fundamental theorem of calculus, says if f is continuous on a closed interval and cap f is an antiderivative of the integrand, then we should be able to do this. We should be able to find the antiderivative and evaluate at the upper bound and subtract that from the antiderivative evaluated at the lower bound, and that should give us the net area. That should give us the answer. All right. It's customary and convenient, right, to denote this difference, right, as using an evaluation bar. And so here's what you'll see, or here's how we'll discuss it, I guess. We have our limits of integration, our bounds. X is a variable of integration. We'll find the antiderivative, evaluate it at our two limits of integration, and subtract them. But here's the shorthand notation for it. Remember, f of x is our integrand. Okay, well, how can we use this? Well, let's just evaluate the definite integral using the fundamental theorem of calculus. You can ignore this graph for right now, and we'll come back and talk about it. Fundamental theorem of calculus part 2 says go ahead and find the antiderivative, so add 1 to your exponent, divide by that same number, add 1 to your exponent, divide by that same number, and evaluate from 0 to 10. You always say that lower bound first and then the upper bound. Let's clean it up. You'll notice that I do not have, I cleaned it up, right? 2 goes into 60 30 times, 3 goes into 6 twice. You'll notice that I did not write plus a constant. We don't need to write the plus constant, and we shouldn't write the plus a constant when we have the definite integrals, right, when we have the bounds. The reason for that is you'll have, basically the constant's going to cancel itself out. I can show you that in just a second, but let me finish this up. All right, so here we would plug the 10 into this problem. You always plug the top number in first, and then you plug the bottom number in, the bottom bound, and subtract those answers. Let's see, 10 squared is 100 times 30 is 1,000. 10 cubed is 1,000 times 2 is 2,000. So you get 1,000 here. So my question, and the reason I said ignore the graph, but you can go look at it right now, is 1,000 the net area? Yes. Definite integrals and net areas are always the exact same thing. Is it the actual area? Well, for this problem it is, because if you look at the graph, every bit of the graph lies above the x-axis between 0 and 10. Everything that we color in is above the x-axis. So yes, this is net area, and this answer is also actual area. That is not always the case. So if you're ever asked to find the actual area, you can use the definite integral, but you have to draw a picture because you won't know if you need to break it apart and look at the things that lie below the x-axis separately from those things that lie above the x-axis. Okay. The reason why we don't need, so this is just an aside, the reason why we don't need the constant is, and I'm making this problem up, but let's say we go from 1 to 5 and we just have something like this, x squared dx, right? We would add 1 to the exponent, divide by that same number, don't forget the constant, and evaluate from 1 to 5. Watch what happens here. I plug the 5 in. Right? And I get plus c. And then I subtract whatever I get when I plug the 1 in. So I get 125 over 3 plus a constant minus 1/3 minus a constant. You see the constants cancel, and that happens, well, let me just leave it like that. That happens every single time. The constants are going to cancel, so you don't need them, so we don't ever write them down. For the definite integrals, we just don't write them down. Okay. Again, we are doing evaluate the definite integral using Fundamental Theorem of Calculus Part 2. Remember, coming back to this problem, just a reminder that 1,000 for this problem was both the net area and the actual area because the entirety of the graph between 0 and 10, right, lied above the x-axis. Look at this one though. Between 0 and 2 pi, some of the graph is above, some of the graph is below. So let's do this definite integral and then talk about its answer. All right, so that 3 can just tag along out front, right? It's a constant being multiplied, so it can just tag along out front. And then you ask yourself, well, what, when you take its derivative, gives a sign as its answer? You should say negative cosine, right? And we want to evaluate this from 0 to 2 pi. First thing we plug in is our 2 pi, and then we want to subtract from that whatever we get when we plug the 0 in. All right, well, cosine of 2 pi is 1. Cosine of 0 is 1. So we end up with a negative 3 minus a negative 3, which gives us 0. Is this our definite integral? Yes. Is it the right answer? Yes. Is it the net area? Yes. Is it the actual area? No. Actual area would have to take into consideration that some of it was below the x-axis, and we would wrap absolute values around that portion so that it returned a positive answer. So this is the definite integral, which is perfect. This is the net area, that's perfect, but it is not the actual area. All right, so we want to sort of revisit that concept. We have the graph of f of x, and you notice how a great portion of it is below the x-axis, so it's going to return a large negative value for this area, and for this little piece, right, kind of a smallish positive value. Region R1, or region 1, is bounded by the curve in the x-axis on the interval negative 1 to 0, and region 2 is bounded by the curve in the x-axis on the interval 0 to 2. I want you to set up, but do not evaluate, the necessary integrals to find the net area of the region between the curve and the x-axis on the interval negative 1 to 2. I'm asking you to set it up but not evaluate. So you don't have to do a whole lot of work here, you just have to set it up, all right? Well, for net area is just your definite integral. You don't have to do anything much. Your net area, your definite integral, is you just figure out the bounds or whatever bounds they tell you, put them on your definite integral, and you're done. You've set it up. I didn't ask you to work it out, I just said set it up. That will find the net area. So the definite integral doesn't care if things are positive or negative, it just sums it all up, all right? Here, though, you're asked to set up but do not evaluate the necessary integrals to find the area of the region. It doesn't say net area, it says area. So in this case, you want to assume that they're talking about actual area. This one's problematic. This one, we have to break into two pieces because if they want the actual area, we cannot allow a portion of it to be negative. So the actual area, we break into two pieces. We go from -1 to 0, and we don't have to do anything with it because it's already above the x-axis and will return positive values. However, from 0 to 2, that guy, because he's below the x-axis, will return negative values. So we are going to have to make sure that we put an absolute value around that piece. I didn't ask you to do anything with it, I just said set it up. You're done. You're done with this. Now, what a lot of students do, I don't know if it's because they're lazy or unhappy or just don't know what they're doing. I don't know. It's very frustrating, but I tell students all the time, hey, if you're asked to find the area, you have to look at the graph. You have to. And if you're at home and every time you're asked to find the area, you pull out your calculator to look at the graph, you're hurting yourself because you're not allowed the graphing calculator on the exam. Most of the time, I'm friendly about it, and I'll actually have a nice problem that's easy to graph, or maybe I'll even have the graph sitting there for you. But you have got to look at the graph. I'm not there to actually prod you and say, hey, make sure you go look at the graph. You're going to have to realize that you have to do that every time. There's no way around it. There's no way around it. You have to look at the graph every time you're asked for the actual area. All right. So now we need to go back to part 1 of the fundamental theorem of calculus, right? We're going to visit that one. And we're going to use that to simplify the following expressions. Well, one thing I want you to see here is I know that this is a part 1 fundamental theorem of calculus problem because it has that ddx out front. Remember, part 1 was the part that related the derivatives, right, to each other. I'm going to do this one the long way, and then maybe we can come up with a shortcut. Okay, so the first thing I want to do is work from the inside out, and the first thing I want to do is find the antiderivative. So I'll add 1 to the exponent, divide by that same number, add 1 to the exponent, divide by that same number. Antiderivative of 7 is 7t, and I'll evaluate this from 1 to x. I'm going to clean it up first. Let's see, so 3 goes into 6, so it's a half. The 3's cancel. All right, and then according to part 2, I plug the x in first. And then I plug the 1 in. And I should get 1/2 x to the 6 plus x cubed minus 7x minus, let's see, this is a half. So it should give me minus, so I'm figuring these out, right? These three added up should give me a negative 11 halves. So minus a negative 11 halves gives me a positive 11 halves there. And now I actually want to do this d dx stuff, where that just means take the derivative. So 6 times a half gives me 6 halves, which is 3. Subtract 1 from the exponent. Let's see, 3. Subtract 1 from the exponent. 7. And then the derivative of this guy is 0. Okay, what is the difference between our integrand and our answer? Well, they're the same, except our answer has x's instead of t's. So at first glance, and this is not quite right, so I'm going to put possible here. I know this thing needs tweaking, but our possible shortcut is just to start off with a problem like this, right, where it's asking us to find the derivative of this definite integral, and just say, well, that's super easy. The derivative and the antiderivative is how a lot of people think of it. The derivative and the antiderivative just cancel each other out, and they leave you with this integrand, except it's evaluated at your variable. Well, this is not quite right. It's close, but this is not quite right. Let's go back up to the fundamental theorem of calculus, part 1. And let me point some things out here. In order for us to use the shortcut that we just talked about, this guy has to be a constant. This has to be a variable with degree 1 and coefficient 1. And then, if those two things happen, then yes, the answer is the integrand evaluated at the variable in the upper bound, right? So if the lower bound is a constant, and the upper bound is a variable with a degree 1 and coefficient 1, then your answer is the integrand evaluated at this variable. Problem is, that isn't always the case. So let's go back to our next couple of examples. So this one is almost perfect, right? They are asking us to find the derivative of this definite integral, and it looks pretty good, except that our lower bound needs to be the constant and the upper bound needs to be the variable of degree 1 with coefficient 1. So this is a pretty easy fix, though. Right, you can flip your bounds, provided that you negate the definite integral, and this negative right here can actually go all the way out front, and so I usually don't even show this step right here. I just usually push that negative all the way through, and now it is written exactly how we need it to be written, and there is no work to do. You just rewrite the integrand, but instead of using t's, you use this variable. You don't write plus c, You don't write dx, you just write the integrand. What has happened here is the derivative and the antiderivative have canceled each other out. It's not really true, but that's how most people think of it. The derivative and the antiderivative, they sound like they kill each other off, right? And in this case they do, except that what you're left with is not the integrand. You're left with the integrand evaluated at x. There is no plus c, none of that kind of stuff. All right. What becomes problematic is when you have this situation, because we have a constant, but our variable is not correct. All right, so I'm going to do the long way of doing this problem, and then we'll come back and tweak our shortcut so that we don't ever have to do the long way again. Okay, I am going to rewrite this just for grins. I'm going to put a little parenthesis in here. So I've got a parenthesis, and then I'm going to put one in here as well. Okay. Now my problem is, I want this to be a variable with a coefficient of 1 and a degree of 1. So I'm going to have to do a substitution. So off to the side, I'm going to come over here and I'm just going to say, hey, I'll make it happen. I will let u equal x squared. But if I do that, then du, think about our substitution rule, right? If I do that, then du is going to be 2x dx. And in fact, we could divide both sides by dx, or we could actually think of this as the actual derivative itself, right? The derivative of u with respect to x is 2x. When we do the substitution rule, right, we would multiply both sides by dx, and we'd get du equals 2x dx. But what we need is this variation, right? We need the derivative. Okay. Well, how does that help? Doesn't help a whole lot just yet. So what else could I do? Well, I could say suppose, just pretend, right? Suppose that y was equal to the definite interval. Then I could replace this x squared with the u that I have up here. Still doesn't seem like I'm doing a whole heck of a lot, and you're probably wondering, well, why are you doing it? You'll see in just a second. Hold on. What I'd really like to do is try to get back to some variation of this d dx stuff, right? I don't have a derivative in here, and I'd like to do that, but hey, this guy, all right, I could not handle him because his variable was x squared, but this guy's variable is u. He is a variable with a coefficient of 1 and a degree of 1. This one, I could take the derivative of and do all that other sort of thing too, and use our shortcut on. So I'm going to be clever about this, and I am going to actually try to find the derivative of y with respect to u. In other words, I'm going to find the derivative with respect to u of both sides of this equation. On the left side, this just becomes dy du, on the right side, the derivative and the antiderivative would cancel out correctly because this is a constant down here. It's just a 0. And the upper bound is a variable with coefficient 1 and degree 1. And so the answer here is just to say, well, the derivative and the antiderivative cancel each other out, and you're left with the integrand evaluated at this variable, which is cosine of u. Right, again, a lot of students are like, well, still I don't see how it's helpful. Okay, so this was just stuff I did off to the side. Come back over to the original problem. Let's fill in what we can. d dx, I don't know what that is, right? I don't have any sort of d dx over here. I'm just going to put d dx down. But this 0 to the x squared cosine of t dt, 0 to the x squared cosine of t dt, that thing is equal to y. So all of this stuff becomes y. So if we look here, what we're actually trying to find is dy dx. Do you remember the chain rule and Leibniz notation? Dy dx is equal to dy du times du dx. Well, dy du is right here. It's cosine of u. We're going to back substitute what u is, times du dx. So u was x squared, and we're going to multiply it by 2x. Okay, so here is the correct answer. What could our shortcut look like? Well, your actual shortcut requires that the upper bound to be a variable with coefficient 1 and degree 1. If that is not the case, then you have to evaluate the integrand at the upper bound variable and multiply by its derivative, right? So if this is not a variable of coefficient 1 and degree 1, then you still do what you would normally do, but you replace this t with this upper bound, and then you come back and multiply by the derivative of the upper bound. Our lower bound must also be a constant. If it's not, then we can manipulate the integral by negating it or by splitting it into two integrals, etc. Right? So there's some other options we could do, but our shortcut now says, yes, you still take this variable and plug it in, but you have to come back and multiply by the derivative of that upper bound. All right, so this should make our life a little bit easier for these next couple of problems. All right, we do have a d dx out here, so this is a fundamental theorem part 1 problem, but it's not set up correctly, right? We have to negate it first so that the 4 is on the bottom. And then we should be okay. Anywhere we see a variable, we're going to replace it with that upper bound. But then we have to come back and multiply by the derivative of this upper bound. So a negative 1 times 6x, so negative 6x over 2 plus e to the 1 plus 3x squared. Pretty straightforward at that point. Okay, again, wrong position. So we have to negate it so that we can flip-flop these. We should be good. We just evaluate at this upper bound. So 4x cubed tangent cubed of 4x. excuse me, but then you have to come back and multiply by the derivative of the upper bound. And so you should end up with, and I am not going to multiply all those out, but you should end up with a negative 4 times 4x quantity cubed, tangent cubed, of 4x. Let's see, 4 cubed is 64 times 4 is 256. So you have a negative 256 x cubed tangent cubed of 4x. All right. Okay, the remainder of these are actually fundamental theorem part 2 problems that require substitution. So you have, I believe, 3 of these. You have 2 ways of handling this, but you have to be very careful. You cannot merge the 2 and somehow mix them together. This is definitely a substitution problem. Remember, with substitution, you're looking for something that when you take its derivative gives you everything else in the problem. There are 2 ways to do this. I will show you 2 ways, and then I will show you what you are not allowed to do. All right, one way you could handle this is you could say, forget the bounds. Let's just do this as an indefinite integral. If that's the case, you would let u equal ln of x. Du would be 1 over x dx. So you would have ln of x gets replaced by u, 1 over x dx gets replaced by du. You add 1 to the exponent, you divide by that same number, don't forget the plus c. Then you back substitute what the u is equal to. Right? Now that helps a little, but it doesn't quite get you the answer. You then would have to come over to the original problem and say, well, I know that the antiderivative is ln of x, quantity squared, divided by 2. And instead of writing the plus c, you would now evaluate it from 1 to e squared. So you would get ln of e squared, the whole thing squared, divided by 2. Then you subtract from it ln of 1, the whole thing squared, divided by 2. Ln and e cancel each other out, leaving you with a 2. When you square it, you get 4. Ln of 1 is 0. 0 squared is 0. So you get 2 minus 0, which is 2. That is one way to do it. It's not the way I usually do it. Here's the way I usually do it, and this is necessary in Cal 2 and Cal 3. There's sometimes where the way we just did it is the best way. There's sometimes where the way I'm about to do it is the best way. You really need to know both. So here we would again say, let's let u equal ln of x. Then du would be 1 over x dx. And then we come back and we change our bounds. These bounds right here are x's right now. If I change my integral to have u's in it, I can't leave my bounds as x's. I will see students do this all the time. It is wrong. You can't do that. If you change this to u's, then your bounds have to change also. So if x equals 1, that's my lower bound, then u would become ln of 1, which is 0. So my lower bound becomes a 0. If x equals e squared, then u equals ln of e squared, which is 2. So my upper bound becomes 2. The reason this is helpful is because in the past where you've had to go back and back substitute your x's, you're not going to have to do that on these problems. You add 1 to your exponent, divide by that same number, evaluate from 0 to 2, plug a 2 in, plug a 0 in, notice I never had to back substitute for the x's because that's actually occurring right here. I'm actually plugging in for x's right over here. So this is the other way to do it, and this is generally how I do these problems. Again, what I'll see some students do, this is absolutely wrong. If you do this, I'm taking off points, and if you tell people I said this is the right way to do it, I will hunt you down because it is not right. Right? Okay, I won't really hunt you down. But anyway, what I'll see some students do is they'll leave this as e squared and 1, then they'll do the work, still leave it as e squared and 1, then they'll back substitute and leave it as e squared and 1, and then eventually they'll plug this in and they'll get the right answer. And then they'll say, well, why did you take off? This statement is true, this statement is true, this is garbage, and this is garbage. So you have a true statement with some untrue stuff in the middle, right? And then you got the right answer. I'm not saying I take off every single point, but I do take points off because you have some garbage steps in the middle that just aren't true, right? It's like you said, apple equals apple equals toad equals toad equals apple. Well, you started off right and you ended off right, but you had some weird stuff in the middle, okay? So you just can't do it this way. You have to choose one way or the other. All right, let's try another one. This is also a substitution. Got to do some algebra for it first. This looks like a tangent inverse problem, but tangent inverse has to have a 1 here, not a 36. So I'm going to factor out a 36. I'm also going to kind of peel this dx off to the side. I just prefer it back here. I'm going to factor a 36 out of each piece. Remember, factoring is just sort of fancy division. So if I'm dividing or factoring out a 36, what happens if I do that? Well, in that first piece, you just get x squared divided by 36. And in the second piece, you get 1. All right, this 1 over 36 can come out front. I'm going to rewrite this piece as x over 6, the whole thing squared. And that should help us a little bit, right? They're both squared, so I can, or they're both perfect squares, so I can write them as individual pieces squared, right? So I come off to the side, and u equals x over 6, or 1/6x. So du equals 1/6 dx. I'm going to multiply both sides by the reciprocal. So I have 6 du equals dx. But if I have, if x equals 0, then I have to figure out what u is equal to. It would be 0 over 6, which is just 0. Oh, okay. And if x equals 6, then u would be 6 divided by 6, which is 1. So I changed my bounds now, or I'm about to. So I have 1 over 36. My old lower bound used to be 0, and it looks like my new lower bound is still 0. That happens sometimes. My old upper bound was 6. My new upper bound is 1. That's fine. My old value here used to be x divided by 6. It's now u, completely fine, plus 1. And dx is now replaced by 6 du. Right, the 6 is just a number being multiplied, so it can go out front. That reduces to 1/6. Tangent inverse of u, and u is evaluated from 0 to 1. I can actually pull the 1/6 out front, and so I only have to worry about tangent inverse of 1 minus tangent inverse of 0. All right, what this is asking you is what angle, when you plug it into tangent, gives you 1 as its answer. You should be telling me pi over 4. And then what angle, when you plug it into tangent, gives you 0 as its answer? And so we end up with pi over 24 as our answer. All right, in the last example, we're going to let u equal 16 minus x to the 4th du would be 4x cubed dx. The 4 is extra, that doesn't appear over here, so I'm going to multiply by the reciprocal. I'm also going to have to change my bounds. If x is 0, then u would be 16 minus 0 to the 4th, which is 16. If x is 2, then u equals 16 minus 2 to the 4th, which is 16 minus 16, which is 0. So my bounds, my old bound of 0 now becomes 16, and my old bound of 2 now becomes 0. I still have the square root. (16 minus x to the 4th gets replaced by u. X cubed dx gets replaced by 1/4 du. I'm going to flip-flop my bounds, and I'm also going to take that 1/4 and throw it out front. So the negative is allowing me to change my bounds, right, flip-flop them. The 1/4 can go out front. The u is getting raised to the 1/2 power so that I can do the power rule properly. All right? So I add 1 to the exponent, divide by that same number, evaluate from 0 to 16. Remember, this 2 can pop up top here. So we have a negative 1/4 times 2/3 u to the 3/2 power, 0 to 16. You do not need a calculator for this. Don't want to hear any whining about it, okay? Because we can do this. We have u to the 3/2 power. There's a couple of ways to write that. Square root of u cubed. Well, that's going to be terrible, right? Because 16 cubed, I'm not doing that, okay? So here's the other way we could write this. We could think of this as the square root of u and then cube it. Those will give me the exact same answer. Well, that's what I want to do because I know what the square root of 16 is. So this negative 1/6 can just tag along out front. I want to find the square root of 16 and then cube it, and subtract from that the square root of 0 and then cube it. Square root of 16 is 4. Square root of 0 is 0. 4 cubed is 64. Minus 0 is just 64. So negative 64/6, that reduces to negative 32/3. And I think I just saw a mistake here. Yep, way the heck up here. Oh my goodness. This negative, right, when I take the derivative, it should give me a negative. So I got to chase this negative everywhere. So that should have been a positive, a positive, a positive, a positive, a positive. Well, you know what? Another way to make it positive is just to erase it. Yeah. So whatever, positive, positive, positive. Geez Louise. Okay, well, we're going to end there. These problems are a little bit more difficult. Certainly, if you have questions, come see me, come talk to me, and I'll help you when I can. All right.